All right. Hi, everyone. Nice to virtually meet you all. And so my name is Ali Mashayekhi. I'm a lecturer at Imperial College London. Before that, I was at Oxford for about a year. And before that, I was at Scripps Institution of Oceanography for about 1 year. And before that, I was a postdoc at MIT for 3 years. And before that, I was at University of Toronto, which is where I did my PhD. And so my PhD was in studying ocean turbulence from more a theoretical end. And then I started applying it to the oceanographic context. And the talk today is going to be something in between fluid mechanics and physical oceanography, which reflects basically my work in different environments over the past decade. So the title is Goldilocks Mixing in Density Stratified Turbulence. These are my collaborators, and I'm going to introduce them at the end. But I thought I'll start from some theoretical backgrounds. So the story of Goldilocks and the three bears, I'm sure you all know. I'm just going to go over it very quickly. It is a British story. It has many different versions. And the latest version, which is one that we can actually tell our kids without traumatizing them, is this one. So Goldilocks was walking in the forest, and she saw a house, which you can see here. She knocked on the door. There was nobody there. She went in, which is totally normal. That's exactly what little girls do on a daily basis. And then she finds 3 bowls of porridge and she starts trying them. One is too hot, one is too cold, but the other one is just right. Then she needs a chair to sit on. One is too high, one is too low. And she finds the one that's the right height. In the process, she breaks one of the chairs. And then she's sleepy. She goes to take a nap. And then there are 3 beds. One is too hard, one is too soft, one is just the right. And that's where she falls asleep. And then at that point, the bears arrive. There's 3 of them, the papa bear, mama bear, and the little bear. And they're obviously confused. Where's my porridge? Why is the chair broken? And somebody's sleeping in my bed. And this version of the story, at this point, the Goldilocks wakes up and leaves, and that's the end of the story. In earlier versions, Goldilocks was the main character was an old lady, and the bears eat her, which would make more sense. So this story poses a number of important questions in anyone's mind, like why do bears need wallpaper, or since when do they actually eat porridge, or why is Papa Bear wearing a bow tie even though he's not wearing an underwear, or what's wrong with Goldilocks? But those are not why I'm telling you this story. The main point to take away from this story is not too hot, not too cold, but the right temperature, not too hard, not too soft, but the right softness. And I will try to convince you that wave-induced turbulence in the ocean, which is very important for a host of reasons, is going to occur statistically and also physically when you have the right balance of stratification and energy available to turbulence. So density stratified turbulence, what I mean by that is that the ocean interior is density stratified, and that stratification gives rise, it helps the system sustain a wave field. Those waves can break, and they go through a hierarchy of hydrodynamic instabilities which exist because of stratification. But if the stratification is really too high, it is going to suppress that turbulence. In the limit of infinite stratification, where you basically tend to a solid state, you're not going to have any vertical motions, right? So, but it turns out that in the ocean, these events happen when there's just the right amount of stratification, not too strong to suppress turbulence and vertical motion, not too small to not give rise to stratified turbulence, but just the right amount. So when I refer to Goldilocks mixing, that is exactly what I mean. Now, a bit of an introduction. So if you think about just the overturning circulation of the ocean actually I have it here. If you think about the overturning circulation, I'm showing you this figure from the review article by Marshall and Spear, it shows the pathways of ocean circulation. It is obviously grossly oversimplified, but the main point is that you have waters that sink at high latitudes where they get cold and salty because of ice formation. They sink to the deep ocean, and they need to come up some way so then you can actually sustain a meridional overturning circulation. Otherwise, the deep oceans would be filled with coldest, densest waters that we couldn't get out. And we know that that's not the case. And so the process that helps bringing those waters up, there are multiple processes, but one of the main ones is the dipycnal mixing, turbulent mixing because of breaking of waves. And these arrows here in each basin show the upwelling of those deep, dense waters to shallower depths. And so mixing is important for closure of the circulation. It's also important if you're interested in various tracer budgets. The nutrients that are important for ocean biology and carbon cycle are rich in the deep ocean and less so at the surface where you have productivity, and how you mix between them, again, depends really on mixing. So basically, a lot of any budget that you pick in the ocean, it is impacted by mixing on some time scale and to some extent. Now, if you zoom in on an area with rough topography, like I'm just doing it here for an example, you can generate turbulence in many ways. First of all, the system is density stratified. So density is highest at the bottom and lightest at the top. And as you go down, it gets denser, but that stable stratification allows for generation of internal waves. So you can get tides going over topography, you can get eddies and jets interacting with topography. All of those can generate waves. And you can also generate waves at the surface through wind interaction or other processes, and all of them fill the ocean with waves that can break. And when those waves break, they can mix. And that's what I'm showing in the bottom left panel. That shows you, that is from a three-dimensional high-resolution observationally forced simulation of the ACC, Antarctic circumpolar flow over the ridges in the Drake Passage. Those are all details that don't matter. What matters is that whenever you see red, it implies water is getting lighter. Whenever you see blue, it means they're getting denser. And when you look at the video, you see that the mixing that I'm talking about is highly intermittent in time and space. So it's a very difficult problem, right? And if you get one of these waves and look at it, it has its own story. And there's no shortage of fluid mechanical papers written on just individual wave breaking. So understanding this problem from a physical perspective and from a larger scale oceanographic perspective is complicated because we are trying to understand a process which is of order of meters that dissipates energy of order of sub-centimeters, and see what it actually means for flows that are occurring on scales of thousands and tens of thousands of kilometers. Now, a bit of background on the oceanographic side before I delve deep into the fluid mechanics part. Going back to the classic paper, the perhaps arguably the most important paper in physical oceanography, at least the most highly cited paper, Abyssal Recipe by Walter Monk. So the idea was that you can ask the question, what is the effective turbulent diffusion coefficient? If you think about mixing as a diffusive process in a Fickian way, what is that diffusive coefficient that would give us the right amount of mixing in the ocean so we get the circulation that we think we can observe? And if you do that, if you play that game, you're going to get a number which ends up being about 10 to the minus 4 in the interior of the ocean. Many people afterwards did the same, and they did it with more details, and they brought in data simulation and observations. I'm showing you one example from Lumpkin and Spear. This is an inverse model estimate of the overturning circulation in the ocean. You see the upper branch of circulation, which goes that way. That's mostly in the Atlantic. That's the deeper branch that has components in all three basins. But what they do in these inverse models is that they chop up the ocean into different boxes, as you can see. And for each box, they try to close the density budget. And through that closure, they infer how much mixing should be there for mass to be conserved. So the diffusivity comes out of the calculation as a byproduct. And when you plot it, again, this is as a function of density, but this would be mid depths of the ocean. You get a number which is about 10 to the minus 4. And that became, a number that people were obsessed with to find in the ocean, and they didn't. There were many field works and field experiments, and they were reviewed nicely, pulled together nicely by Amy Waterhouse and others, and is now available through a database actually. But when you start looking at them, what you find is that turbulence is really bottom enhanced. Here I'm showing you rate of dissipation of kinetic energy, but if you also look at the diffusivity, it is really bottom enhanced. And note that this is in coordinate of height above the bottom, because at least my interest in this problem comes from understanding deeper branch of circulation. And so I'm more concerned with turbulence that's generated at the bottom. So height above the bottom is the right coordinate to look at. And if you look at diffusivity there, over smooth regions, over rough regions, and over ridges, which generate a lot of turbulence, what you find is that away from topography, you don't have 10 to the minus 4. You have an order of magnitude less, but near topography, diffusivity mixing can get much higher. It can be an order of magnitude larger. And so this was an observation that, in the 90s, we started having observations that would show this bottom enhanced mixing and turbulence events through observations. Brazil Basin was the example that actually made this big news. And if you look at the decay scale of turbulence, you see the same picture. Globally, now we have theoretical models that help us basically build these maps. Like if you look at the middle of the Atlantic Ocean over the mid-ocean ridge, you see that the decay scale is very small, and away it is larger. What this is trying to say is the same as that, which is that where you generate a lot of strong turbulence, like here for tidal reasons, when turbulence is really strong in the deep ocean, it's going to decay really rapidly. And when it's weak, it's going to more or less be uniform in the vertical. Now, why am I saying all of this? Because the key is that turbulence is bottom enhanced. It has a very sharp decay when it's really strong, and that has implication. So in the past, I would say since 2015, the past 5 years, there has been a new paradigm of ocean mixing and its role in the ocean circulation that has come sort of popular. And that's, I refer to it as boundary upwelling, interior sinking, and this is what I mean. So if you go back like 10 years and read papers and textbooks on physical oceanography, we generally say that internal wave field in the ocean, they can provide mixing through breaking, and that brings deep waters up. That was the classical way of thinking about it. But if you think about an element of fluid in the ocean, like you can see in the top left panel here, if mixing is bottom enhanced, which we think it is, then this is going to mix more with waters below than waters above. So over time, preferentially it's going to get denser, and it's going to sink. And then if it's right at the boundary, it's only going to be mixing with waters above, so it's going to get lighter over time. So as a result of that, in this paradigm, if you have a mixing that's bottom enhanced, you're going to get waters sink, and then at the boundary, they start crawling up. And that's what is shown here. They sink and they go up. If you can more formally and mathematically formulate this, and this is what turns out to be the case. If you look at the bottom left, I'm calling the upwelling or downwelling as E tilde, but it is basically the vertical divergence of the density flux, which is this term. So from observations that I showed in the previous slide, we think of this density flux as being bottom enhanced, but at the very bottom, it has to go to 0 because the flux is 0 at the solid boundary. And since the sense of upwelling or downwelling is set by this divergence, away from the, sort of in the high mixing region out of the bottom boundary layer, you get a downwelling because mixing is increasing with depth. And after that, it changes sign, the divergence changes sign, and you get upwelling. Again, this is just connecting the small scale mixing to the bigger picture. But the point is that there is an expectation that the divergence of the buoyancy flux changes sign at some point, as you approach a solid boundary. And that change of sign implies that you go from downwelling of waters to upwelling of waters. Now, the buoyancy flux can be approximated as a gamma times epsilon. Epsilon is the rate of dissipation of kinetic energy, is something that we can infer from measurements directly. Mixing isn't. So that's why we measure epsilon, then say that the buoyancy flux is epsilon times a coefficient, which we refer to as the flux coefficient, or gamma. I'll tell you where this comes from shortly, but this is a reduced version of the turbulent kinetic energy budget based on a number of assumptions. But this is the working model in physical oceanography. Now, the point I'm trying to make is that even though this is not what I'll be talking about, but if someone like me wants to understand the patterns of upwelling and downwelling in the ocean and what it means for circulation and tracer budgets, one of the things that you're interested in is how the divergence of the buoyancy flux varies in space. What is its divergence, and when is it going to be positive or negative? So where are you getting upwelling or downwelling? And this is what we approximate with this, and this is epsilon is what we measure. So this gamma, the flux coefficient, is where the physics of turbulence lies, and that's what I want to understand. How does this vary as you go from away from topography into the boundary layer and to the boundary where it vanishes? The variations in that has to basically give us the upwelling and downwelling, because we have the expectation that the flux is going to increase towards the bottom because turbulence is bottoming has, but we also have the expectation that within the boundary layer, the flux has to go to zero, right? And that is what the flux is expected to do, but that is not what we observe in epsilon, because epsilon keeps increasing almost all the way to the bottom. So epsilon is the rate of dissipation of kinetic energy. You can have boundary turbulence even without stratification, right? So this shouldn't necessarily go to zero towards the boundary, but as you go into an unstratified boundary layer towards the seafloor, even though this remains finite, this has to go to zero, because when you go to the limit of no flux and no stratification, then you're not going to have any mixing. So this is what I'm going to talk about quite a lot from now on, but this is the context and why we actually care about it. So what are the key questions? I think it is very interesting that we are still at the stage that we're arguing, are things going up or down? That says that we're still at level of basic understanding in terms of role of mixing in ocean circulation. Role of topography, as you can imagine, is significant. That is not what I'll talk about. I'll focus on how to relate small scale mixing through gamma to this picture. And just before doing that, just to prove as a proof of concept, I can do something very simple. I can say we have ways to construct the tidal energy in the ocean and distribute it over the water column. And we have an idea of the stratification in the ocean from climatology. I can put them together and I can calculate the upwelling and downwelling patterns. And the way I can do it is that I can calculate the tidal mixing and how much it creates downwelling. And in that calculation, I have to assume that at the very bottom grid cell on the grid that I'm doing the calculation, the flux has to go to zero. And that is how I can infer the rate of upwelling, which is these red that you see around rough topography. So what I'm trying to say here, what I was trying to say is that we don't still fully know the physics of boundary layer turbulence, but we have a grip on how much tides and other processes can push waters down due to downwelling. And we can use that and conservation of mass, basically saying what goes down has to come up. And through that, we can infer how much waters can upwell along topographic features. And if you do that and integrate it globally for different density levels, you can think of these as depth levels. Density levels are, to some approximation, sort of horizontal. The point is that this is transformation rate, basically the diffusive mixing across the density level. The main point here is that you get a lot of upwelling in sharp boundary layers, and you get broader downwelling away from topography. In the net, you get a net upwelling. So the actual diffusive driven component of the circulation is a residual of larger contributions that are of opposing signs. Now, I'm going to talk now for the next 10, 15 minutes about, for the next 15 minutes, 20 minutes about the physics of stratified turbulence and how we can constrain gamma better. And then I'll, at the end, if there's time left, I'll try to connect it back to the big picture. But the point is that the reason I went through that introduction was to make the point that even though gamma and mixing efficiency has been a topic of research for a long, long time and is fundamentally important for a host of problems, my interest in this problem is coming from the fact that I really needed to sort it out to be able to understand how it helps close the circulation of the ocean and also how it helps with the nutrient budgets. So most of my arguments are motivated, driven, or geared towards that conversation, but you can be interested in wave breaking and mixing for entirely different reasons. So that's a caveat I wanted to put out there. So it's very basics. I'm trying to avoid as much as I can equations. So if I write down the turbulent kinetic energy budget for a wave that is breaking, and this is sort of a time evolution of such a wave, this is a classic shear instability. You can think of the colors as temperature or as density. The point is that this is denser here, this is lighter, and you mix it, and at the end, you have a region that is mixed of intermediate density or temperature. Now, I can write down the turbulent kinetic energy budget, and these terms have mathematical representation, which we don't need to worry about, but this is the total turbulent kinetic energy budget. It's normalized, and its time evolution depends on a number of terms. This first term is the turbulent production. That's how turbulence extracts energy from the background shear, which is the source of its energy. And let's look at the last two. This one is the buoyancy flux, the density flux. That's basically the effective vertical flux due to breaking of the wave. That's the mixing that we're interested in. And this is viscous dissipation, the rate of basically viscosity dissipating energy into heat. And there are two other terms, and those terms represent exchange of energy between the background flow and turbulence through this intermediate wavy thing. Now, the working model in oceanography is due to Osborne, which is much reduced, which is based on assuming that turbulence is stationary, so we get rid of that, and that there is a separation of scale between the background flow and the small scale turbulence. So it basically ignores this intermediate wave scale, and that takes care of those two other terms. And then you end up with three, which says that there's some energy provided to turbulence from the mean shear that extraction is done through the Reynolds stresses, the shear production term, and that gives rise to some mixing and to some dissipation. You can rearrange this, and if you do it, you end up getting this equation, which is what I said before. Kappa is the diffusivity, gamma is the flux coefficient, epsilon and n are basically rate of dissipation of kinetic energy, and this is the buoyancy frequency, which is basically the vertical density gradient. Now, this is very popular because we can use it operationally. We can infer this from measurement. We can measure the stratification. We can assume that stratified turbulence doesn't matter, so we assign a value to it, typically 0.2, and then we have a diffusivity. But that has limitations, and those limitations has kept us from understanding upwelling, downwelling patterns close to boundaries. So that's why we're trying to unravel this and dig deeper. Now, some very basic definitions, so I can construct a model for mixing efficiency, the same wave. Let's define a number of length scales of turbulence. The Kolmogorov scale is the scale that basically beyond which dissipation takes energy out of the system. Now we have the Osmedov scale, and you can think of the Osmedov scale as the scales of largest turbulent eddies that you have. And then we have the Thorpe scale, LT, which is the source of energy, the scale of the source of energy in the system. I can explain them using the graphics. If you look at this wave, this rolls up, and you can think of the size of this as your Thorpe scale, if you like. And that would be because when you do this roll up, you get dense water, you lift it into light water. That stores energy in form of available potential energy. So that is this LT is a representative of source of energy. Then once you have that energy available, little eddies can feed on it and grow. And those, the size of those, you can think of as your Osmedov scale. And those grow, they basically suck energy out of the reservoir until there is a state that those eddies, LO, Osmedov scale eddies, have the same sort of size as the LT, as the original wave that contained the energy. And then beyond that, both of the scales decay. And so the evolution of those scales is shown here, but let's focus on the right panel. The key point is that LT, or the size of the original parent eddy, is initially large, but turbulent eddy size LO is small, but it feeds on LT until a point that the two are the same, and then they decay, but at different rates. So this phase, I'll argue, is the Goldilocks phase, because when the little eddies grow as large as the original eddy, they can extract energy from the mean shear most efficiently. And that's the phase that you actually get very strong, energetic, and efficient mixing. So those are the formal definitions. You can define a buoyancy Reynolds number as epsilon over kinematic viscosity times n squared. This is referred to in the field as the buoyancy Reynolds number. We can also write it as the ratio of the Osmedov to Kolmogorov scale, and that makes it easier to interpret, because Osmedov scale is the upper bound of your inertial subrange. That's the largest turbulent eddies that you have. Kolmogorov scale is the other end, and the larger the ratio between them means the broader your inertial subrange. So the larger this number, the more energetic your turbulence. The larger, the wider the turbulence spectra. So in that sense, it is a Reynolds number. And of course, you have the Richardson number, which is a stability criteria for shear-induced turbulence. Now, again, another basic definition: efficiency of mixing is M mixing, the buoyancy flux, divided by the total energy, the total production energy that goes to turbulence, which is the sum of mixing and dissipation. So this is a true efficiency between 0 and 1. But operationally, as I said, we usually use gamma, which is the flux coefficient, but gamma is defined as epsilon over 1 minus epsilon. So, or if you rearrange it, gamma is the ratio of mixing to dissipation. So efficiency is a better thing to work with because it's an efficiency, it's between 0 and 1. But as I said, we typically use this one, and keep in mind that gamma can be, theoretically, it can be 0 or it can be infinite, right? Because you can tend to a limit of no turbulence in which dissipation of kinetic energy goes to 0, but still you have molecular diffusion. It's very small, but it's non-zero. But this can theoretically get very, very large. So there has been a lot of work over the past decades on how we can parameterize mixing efficiency. One of the parameters that people have tried to do it against was being the buoyancy Reynolds number. And if I plot the data from turbulent patches from different oceanic experiments, this is usually what we end up getting. So these are 6 different experiments. I'm going to explain them very briefly because that's what I'll be using. Brazil Basin, tidal mixing, the deep Brazil Basin, do more in the Brazil Basin, but these mixing in the canyons in the Abyssal Ocean. Samoan Passage off the coast of Samoa, 5,000 meters deep, is hydraulically controlled turbulence as flow goes over 2 consecutive sills. These 2 are more tropical and upper ocean, shear-induced, on the equatorial undercurrent, and off the coast of California. These are more shear instability-like processes, and this is off a ridge in the Japan Sea. And parametric subharmonic instability is believed to be the case. So those are all details that don't matter, but the point is that there are different turbulence generated through different processes, different parts of the ocean, and that might explain that, okay, that's maybe why if I plot data from that is all over the place. So there are many blue dots here, and each dot is one patch identified for one of these experiments. And the lines are being averages for each experiment. The point is that if I plot them as a function of buoyancy Reynolds number, there's no reason we can convince ourselves that we can parameterize this in a successful way. So that's why we revisited this problem and tried to parameterize gamma in a new way. And it turns out you can actually do it in a very simple way that seems to work universally. And the ingredients are very, very simple, and 3 that we're used to. The first thing I'm going to use is just the assumption that there is an inertial subrange, there is a forward cascade of energy. Going back to Kolmogorov and Taylor, the idea is that you have some, you have a range, you have some largest eddies that contain the energy, and then there is a forward cascade of energy all the way to very small eddies, where at which dissipation due to viscosity becomes dominant and takes the energy out of the system. If you make that assumption, you can write this, you can easily, based on dimensional arguments, come up with this equation, which says that the largest eddies that inject energy into your turbulence are proportional to turbulent kinetic energy to this power divided by rate of dissipation of kinetic energy. So that's the first assumption. The second is Prandtl's mixing length theory, which says that imagine there is a steering mechanism that is mixing, and in our case, that would be the original wave that rolls up and starts steering. You can write that, you can quantify the net diffusion due to that through, you can write that diffusion as proportional to a mixing length, which is basically what is set by the steering mechanism times the turbulent kinetic energy, square root of that. So that's again the classic mixing length. And the other one is the Osborn relation, which we've seen already a number of times, which comes from the turbulent kinetic energy. These three, very trivial, you write them, you can combine them into one. And I'm using M as a subscript for gamma to make the point that I'm now still talking about the accurate gamma that comes from accurate mixing. And I use it because when I compare it to observations, I refer to it as a different gamma, because in observations, we infer gamma from comparing mixing of the momentum and mixing of temperature variance. I'm not going to go into those details, but my point is that you can measure, infer, or estimate gamma different ways, and that's why I use different subscripts. But for this talk, we can think of all of them as the same thing, just for simplicity. So if you combine those three ingredients, you're going to get gamma as proportional to the injection scale, the mixing length, and the Osmedov scale, which is the basically Osmedov scale physically represents the size of the eddies that the largest eddies that are not suppressed by stratification, right? So because we were talking about density stratified turbulence, and as I said, stratification suppresses turbulence. And so Osmedov scale are the largest eddies that they're not still feeling the stratification. Anything above that is going to feel the pressing of stratification. So we can combine them into this, and once we have it, we can come up with a few interesting limits. First, let's imagine that you have a limit. Because I'm applying this, I want to apply this to turbulent patches from observations to see if it makes sense. So let's imagine we have patches that are corresponding to young turbulence that's growing. In that phase, the Thorpe scale, the size of the original parent overturn, is larger, much larger than the size of the little overturns that grow within that, because turbulence hasn't still fully developed, it is growing. So it makes sense to use LT as a mixing length. And if you do it and put it in there, you are going to recover one scaling relationship in terms of LT over LO. ROT, sorry, I forgot to define it. It's just the ratio of the Osmedov scale to Thorpe scale, right? Because those are the two scales that I care about. There is another limit, which is the limit when the turbulence is decaying, or people sometimes refer to it as fossilization phase. In that phase, LT has decayed, right? Because the original source of energy has run out. It's been sucked out of it into turbulence, gone to mixing and dissipation. But because it's fossilizing, LT has decayed, but LO is decaying slower. In this phase, LO is not an actual physical scale, but it is the largest scale that doesn't feel the stratification, isn't suppressed by stratification. But the actual eddies aren't of that size, they're of size of LT. So LO is the potential. It is how large the eddies could grow if we kept pumping energy into the system. But we are not, because it's fossilizing, because it's decaying, because these, which are physical oceanic turbulent events, they grow, boom, you get a burst, and then they decay. They run out of energy. And so LO is the potential that the eddies could have and grow, but they don't achieve that because there's not a continuous injection of energy into it. So in that phase, LT is much smaller than LO, but because the effective length scale of the largest eddies is LT, because that's whatever energy is left, both of these scales injection and mixing length becomes LT. And so this relationship basically finds another form. So I don't mean to make it confusing, but what I'm trying to say is that if we use mixing length theory, inertial subrange, and the Osborn relation, we get this. And then you need to make an assumption. What is injecting energy into the system and what is mixing? In early phases of turbulence, mixing is by the parent patch, which is not turbulent. It can be more laminar, but it's down the mixing length. But it gives you the mixing length, but the actual upper bound of your inertial subrange is the Osmedov scale. But in the fossilization phase, the Osmedov scale is the potential, but not the actual size of the eddies. The actual size is the Thorpe scale. So both of them become the Thorpe scale. So that's why you get two different relations. Now you can combine them into one relationship of this form, and that relationship can be visualized if I plot it as a function of the Osmedov to Thorpe scale. When in early phases of turbulence, Thorpe scale is much larger than the Osmedov scale because you have the overturn in place, but the turbulence hasn't still grown. In that phase, you're going to have the first scaling, ROT to the -1, and that would be that line, that's that branch. And in the fossilization phase, you get the other scaling, which is to the -4/3, and that's where LT is very small and LO, which is the potential that eddies could have, is larger. And you combine them and you get this black line. So this is for gamma. I could actually do it for mixing efficiency because they're related, and would get the red line. And that's basically showing that as you go to young turbulence, efficiency becomes perfect. In the limit of no turbulence, you have perfect efficiency because it's molecular mixing, no viscous dissipation, efficiency is exactly 1. It doesn't really matter. It's really efficient, but when there's no turbulence. In the other limit, where turbulence decays, there's no mixing and there's no efficiency because everything has basically decayed. So now this to the power of -4/3 existed before. This is sort of new, this one, but the newer thing, the more important thing is that where they come together is here, is when ROT, the ratio of Osmedov and Thorpe scale is around 1, and that is where you get the most effectively efficient mixing. Why do I say most effectively? Here you can get large mixing, but there's nothing, but you can get very efficient mixing, but there's not much turbulence, right? So there's no turbulent flux, it's just molecular efficient mixing. Here, turbulence has decayed, and so there's not much energy to mix. In the middle here is where you have enough energy and enough turbulence that you can effectively mix and get an effectively large turbulent buoyancy flux. So that's why we call this Goldilocks mixing. It's not too hot, not too cold, and it is just the right temperature. Now, I can apply this to those oceanic data sets that I talked about, the 6 cases. And for each of them, it matches very well. So the blue is the data, the red is the parameterization, and the solid line is the previous scaling that was previously offered. I forgot to say one thing. There is a coefficient here, A. It's about 1/2 to 2/3. I'm not going to go into details of where it comes from, but it's very closely related to the stability criteria of shear instability. So if you assume that the Richardson number of a quarter gives you a stability criteria, you can get that from that to be about 1/2. So everything here is coming from theory. Even that quarter value of quarter for shear instability, you can get it theoretically. So these are all based on simple theoretical tools, and we get a parameterization that doesn't need any tuning. And when you compare it, it agrees well with all of these data. I can show the agreement better here, where I combine all of the data. We have about 36,000 turbulent patches, and blue is the bin average data, and red is our parameterization. It is really as good as it gets. And I can plot the ratio of parameterization to data for different cases, and you can see there's a clustering around log being 0. So I'm very happy with this, especially considering that I was actually comparing it with this, right? So this was where we started from, and now we have managed to collapse everything onto here. So all happy about that. I'm gonna skip this. But now, does any of this actually really matter? It depends on what you mean by matter. Let's try to come up with a few ways to measure that. One, let's assume what we're interested in is the net turbulent flux. net buoyancy flux, just as one measure. It depends on what you're really studying the turbulence for. That answers the question, what is it that you want to know if all of the mixing efficiency arguments matter for or not. But I'm interested in buoyancy flux and its divergence. So if I get the data that I showed you and calculate the buoyancy flux, basically estimated as gamma times epsilon for them, this is what I get. So this is from all of the data piled together, and this is the PDF of the data, and I have different measures of the flux. So this is the accurate epsilon times gamma, because the data that I'm using has gamma inferred from observations. And then there are different measures. This is if you just go with 0.2, and this doesn't really matter. The point is that if you just compare the green line, which is 0.2, which is what people usually use as a constant, or if you use the black line, I want to compare those two. And we have one that we parameterize, which would be the blue line. So the blue line, the black line, and the green lines are the ones that show the difference. But if you look at this, you might say that, well, this doesn't really matter. But the point is that this is highly skewed, right? And we're talking about something that's orders of magnitude. This is 6 orders of magnitude difference. And the tails really matter. The tails are very big waves that do a lot of mixing. And so if I could zoom in, the differences between those would really matter for the tail, and they are significant. But one way to quantify that is that I can just add the buoyancy flux for all of the patches. And so I'm plotting the cumulative flux normalized by the total flux for all of these. And so at the end, what you get is basically the total mixing integrated over all the patches. And the point is that if you go with the previous parameterization offered, you can overshoot quite a bit. And within that, you can be off by a factor of 2 to 3, which is, you can easily be off 100%, 200%. So all of this actually really does matter. But some other interesting things come out of just playing around with this data. So if you look at the bottom right panel, this is all the data, the histogram, 2D histogram of the ROT, ratio of Osmondov to Thorpe scale, as a function of epsilon. And it shows that the largest overturns that dissipate a lot have an ROT which is around 1. So what that means is that when waves are really energetically dissipating, they are in the Goldilocks phase. ROT is around 1. When you go away from that, you get a scatter. But that's because some of these low epsilon cases are because they're young turbulence. Turbulence is just growing. And some of them are decaying turbulence for which it is fossilizing. And those have very different values of ROT and gamma. So you can think of all the old and young piled up here, but this is the Goldilocks phase. That collapsed into the Goldilocks phase for larger patches that actually do matter in an integrated sense, because they do most of the damage, is actually fortunate because we can exploit that further. So all of that, now I'm gonna, in the next few minutes, I'm gonna have another 3 minutes and I'll finish. I'm gonna try to see how we can connect this back to the big picture. So the parameterization is something that we submitted recently, and now we're in the process of applying it to the bigger picture. So everything now on is going to be very much work in progress. So if this is a part of the Southern Ocean showing vertical shear, again, emphasizing that turbulence is highly intermittent in time and space. And as a review, we said that if you get one of them and look at it, there is an evolution in terms of the life cycle, but there is a phase where LT and LO are sort of the same, and that is the Goldilocks phase of turbulence. Now, if I start looking at the data of the ocean data, I see something very interesting. If you look at the top right panel, forget about the left one. If you look at the top right panel, this is showing histogram of ROT from data, from different experiments. The bottom left panel is for the 6 experiments that I showed you before, 4, 5, 6, actually 8. And all of them, if you notice, have a histogram that centers around ROT being around 1, right? And if you look at it more carefully, if you put all that data together and plot the PDF, but then do it for different quartiles of epsilon, you see that as you go to higher and higher values of epsilon, this is the top quartile of epsilon, the peak gets closer to log 10 being 0, meaning that ROT is around 1. So that again emphasizes what I said for a much larger database, that as you go to energy, for the most energetic turbulent events, you have the Goldilocks mixing. And we know that for that, we have a parameterization that works perfectly well. So now the question is, why is it that you have very efficient mixing when you have, why is it that most of the patches we observe are in this efficiently mixing Goldilocks phase? And that's something that we are now trying to understand from a statistical perspective. And in interest of time, I'm not going to get into that, but if somebody asks a question, I'm going to come back to it. Now, I want to finish by this point that we have done some preliminary work, we're fine-tuning it. But if you apply this parameterization to a global picture, you get something very interesting. You find that gamma, in a bulk sense, not for one patch, but let's say for a box, for a grid cell of a climate model, 1 degree by 1 degree by 200 meters, like which includes many, many patches. The effective bulk gamma for that can be very high. And it can be very high in regions that is weak turbulence, right? It's not high because it's very effective. It is high because, as you learn, you can have very high gamma when there's not much mixing, but that doesn't really matter, right? And those are the orange parts. But when you get close to topography where you have very strong turbulence, you get gamma, which ends up being around the Goldilocks phase. And as I've shown, these variations in gamma really actually matter because they set the divergence of the flux and the upwelling and downwelling patterns. And then what you can do is that you can do this calculation and identify the upwelling, downwelling regions and ask the question, what is the thickness of the upwelling zone in the deep ocean? If we do it using our parameterization, we get this picture in the top right. This is the thickness of the boundary layer within which waters are upwelling. Bottom is the same thing diagnosed from data, but this is from CTD, from hydrographic sections. This is basically looking at all the CTD profiles in the ocean that measure density, and through that finding the thickness of the bottom boundary layer. So this is a direct observation of the boundary layer thickness. And we sort of start recovering the same pattern. Had we gone with a constant gamma of 0.2, we wouldn't get any of this pattern. Absolutely not. We just get a constant, which would, so we wouldn't be able to resolve the bottom boundary layer. So the fact that these two start looking the same makes me think that we're on the right path, but we still have quite a bit of work to do in the next few months to pull this all together. So with that, I'm going to finish this with credits. I drew on information from a number of papers that can be found on my website. Some are submitted. If you're interested, email me. I'll be happy to share a draft with you. But I worked with Colin Caulfield and Matthew Alford on the parameterization part. Laura Chimoli has helped with implementing them in the global calculation, getting the boundary layer turbulence versus interior mixing, the last slide that I showed, and Bibi Kell at the National Oceanography Center in Southampton is helping me figure out how to connect the microscale physics of turbulence to the larger scale implications through statistical tools. Thanks for listening. I'd be happy to take questions.